Welcome to this explainer. Today, we're going to uncover the absolutely fascinating engineering that allows continuously rotating machines to transfer power and data without, tangling their wires into a chaotic mess. It's this whole hidden world of electromechanical design that literally makes so much of our modern technology possible. So let's dive right into the core engineering problem here. How exactly do you transmit electrical power, pressurized fluid, and high-speed data into a continuously spinning object? Think about a military radar dish sweeping the horizon, or a medical CT scanner diagnosing a patient, or even just a helicopter rotor spinning at high speeds. If they were simply hardwired, those cables would snap in seconds. So how on earth do they do it? To answer that, this explainer is going to quickly cover 5 key areas: solving the rotation problem, the anatomy of a slip ring, electricity versus fluid transfer, high-speed optical transmission, and finally, advanced real-world applications. Section 1. Solving the rotation problem and anatomy of a slip ring, the basics of electromechanical interfaces. Let's begin our journey by looking at the foundational component of rotational mechanics. Now, what's really amazing here is the sheer simplicity of it. A basic slip ring essentially relies on a stationary brush making physical contact with a continuously rotating ring to pass current. That is the core concept right there. The brush just slides along the outside diameter of the ring, forming this continuous electrical connection that allows current or signals to pass right through the rotating gap. If we want to formally define it, a slip ring, which you might also hear called a rotary electrical interface or a collector ring, is an electromechanical device that assists in transmitting power and electrical signals from a stationary structure to a rotating assembly. It basically functions as the crucial pivot point, making uninterrupted electrical communication possible in environments where unceasing spinning is just the norm. But, as you can probably guess, looking under the hood, a slip ring is way more than just a wire dragging on a circle of metal. These assemblies are organized based on space constraints, so the design can be integrated into a compact, enclosed capsule complete with bearings, or it can actually be separated into individual rotor and brush blocks to build directly into an existing mechanism. Depending on how much physical space you have to work with, engineers generally rely on 2 main configurations. The traditional drum approach stacks rings adjacent to one another along a center line, kind of like the threads on a bolt. But if your length is restricted, you use the pancake approach, which places rings concentric with one another, much like the grooves on a vinyl record. This allows the slip ring to fit into incredibly tight spaces on the vertical axis, though I should mention this can sometimes increase the risk of crosstalk or debris collecting. So here's the catch. While the concept is simple, the execution is incredibly complex. Engineers have to carefully manage contact resistance to minimize electrical noise. Even microscopic vibrations or a tiny microgap can cause voltage fluctuations. On top of that, materials like copper and silver can oxidize over time, and environmental contaminants like dust, moisture, and heat can absolutely destroy your signal integrity. Maintaining a clear connection over millions of revolutions is, for sure, an absolute masterclass in material science. Moving on to Section 2. Electricity versus fluid transfer, expanding the rotational interface. Let's see how this builds when we need to transfer something other than electricity. Because let's face it, machines don't just run on wires. When a system requires the passage of fluids under pressure or a vacuum, we're talking steam, thermal oils, water, gases. We cross over from electrical engineering right into mechanical engineering. If a slip ring is this electrical marvel relying on touch technology, a rotary joint is a mechanical masterpiece. It relies on extremely complex mechanical bearings and highly resilient pressure seals to seamlessly pass fluids from a static line right into a rotating part without leaking a single drop. But what happens when you actually need both? Well, a lot of times, these technologies are combined into a single, highly efficient unit. You pair the electrical prowess of a slip ring with the hydraulic or pneumatic efficiency of a rotary joint. The result? A perfectly versatile, controllable system that's absolutely ideal for complex robotic arms or automated manufacturing equipment that needs power, data, and hydraulics all at the exact same time. Section 3. High-speed optical transmission. Enter the forge. So, what happens when we need to transmit massive amounts of digital data, like uncompressed HD video or complex radar feeds, without any electrical interference? Because traditional copper rings, they can definitely hit a bandwidth wall. The solution here is the fiber optic rotary joint, or FORJ for short. This is basically the optical equivalent to an electrical slip ring.
Instead of passing current through a metal brush, a forge allows an optical signal, carried by light, to be transmitted right across the rotating interface. This maintains the intrinsic, super high bandwidth advantages of fiber optics end to end.
And forges are absolute game changers in modern engineering. Why? Well, first, they suffer zero electromagnetic interference, or EMI, making them perfect for really noisy military or industrial environments. Second, they offer practically unlimited data bandwidth. Third, there is absolutely no crosstalk between fiber lines. And finally, they can be built in simple, single-pass configurations or incredibly complex multi-pass configurations that require laser-precise mechanical alignment to keep multiple light beams perfectly coupled as they spin. This right here is the ultimate synthesis of everything we've talked about so far. In an integrated motion assembly, you've got a drive motor and resolver right in the middle, flanked by a fluid rotary union for liquids, an electrical slip ring for power, and stacked on the very end, a fiber optic rotary joint, handling all that multiplexed, high-speed optical data, all working seamlessly together in one rotating package. It's truly a marvel of modern design. Section 4. Advanced real-world applications, where rotational interfaces matter most. Now that we deeply understand the technology, let's explore the extreme environments where these devices are absolutely critical. This is where the engineering truly meets the real world. Prioritizing noise-free signal transmission is completely non-negotiable across multiple massive industries. Think about medical imaging, like the CT scanners we rely on for life-saving diagnostics. Slip rings there have to transmit HD video and power, entirely free of EMI to prevent video dropout. Or in wind turbines, providing clean energy. They have to survive incredibly harsh environments while passing power and SCADA data. And in industrial robotics, ultra-low latency is strictly required for precise servo control. Look to the skies, and you'll see the aerospace sector relies heavily on these interfaces. Advanced military helicopters use them practically everywhere. We're talking from the main and tail rotor de-icing systems to flight controls, right down to the forward-looking infrared targeting turrets on the chin. Systems like the F-18's ATFLR or the F-16's sniper pods utilize slip rings to allow continuous rotation in the roll axis. It literally allows pilots to see in the dark without tangling the camera's wires. Moving from the sky all the way down to the crushing depths of the ocean floor, combined slip rings and FORJs are just as vital for marine exploration. They allow remotely operated vehicles, ROVs, to transmit high-definition seismic surveying data, miles up a tether to floating production, storage, and offloading vessels bobbing on the surface. And these units have to be incredibly rugged, often sealed to strict IP68 standards, just to keep out the highly pressurized saltwater. Ultimately, designing a successful rotational project isn't just about grabbing parts off a shelf. You have to optimize 4 interconnected engineering domains. First, the transmission channels. Basically, how much data and power do you actually need? Second, the physical connectivity itself. Third, the protective enclosure to combat dirt, mud, and water. And fourth, the required rotational speed and duty cycle. From rudimentary copper wire brushes dating all the way back to the Industrial Revolution, right up to laser-precise fiber optic joints transmitting gigabits of data, the evolution of the slip ring is just an incredible testament to human ingenuity. It constantly pushes the boundaries of what automated, rotating machines can achieve. So, what rotational engineering marvel are you going to build next? If you found this explainer helpful in grasping the complex and fascinating engineering behind rotational interfaces, please like, share, and subscribe to @MakersJunction on YouTube for more highly professional, basic to advanced engineering content. Keep exploring, keep building, and we'll see you in the next explainer.